Hi everybody, welcome back to another video on Feynman integration. They will be evaluating the integral from 0 to pi of 1 over 2 minus cosine of x all squared dx. I think you can do this one without Feynman integration, but it's pretty difficult, I think. I didn't actually try, but it seems like it would be. So the first thing we'll do is create a function of t, and it'll be equal to the integral from 0 to pi of 1 over t minus cosine x dx. And you'll notice that I did not square it. Next thing we'll do is we will perform, we'll do the tangent half angle substitution that I've gone over in a previous video. The tangent half angle substitution is just u is equal to tangent of x over 2. And what you get, if you make that substitution and follow the, the steps in the Weierstrass substitution, you get that cosine of x is equal to 1 minus u squared over 1 plus u squared, and dx is equal to 2 over 1 plus u squared du. So there it is. There's our substitution applied to f of t. Our bounds of integration will change to tangent of 0 over 2, which is 0, and tangent of infinity over 2, which is tangent of infinity. Tangent of 0 over 2 will be 0, but tangent of pi over 2 is infinity. And then we'll get 1 over t minus, there's our cosine x right here, 1 minus u squared over 1 plus u squared, and there's our dx right there, which is 2 over 1 plus u squared du. And then doing a little bit of rearranging, basically you just distribute this 1 plus u squared into the denominator here and bring the 2 outside, and you get this. Then you distribute all this and rearrange it and factor out a u squared, and you'll get f of t is equal to 2 times the integral from 0 to infinity of 1 over u squared times t plus 1 plus t minus 1. And then doing a little bit more, and then simply factoring out a 1 over t plus 1 will give you that f of t is equal to 2 over t plus 1 times the integral from 0 to infinity of 1 over u squared plus t minus 1 over t plus 1 du. And this should be a familiar form to you, so I'll just let you do the integration from that point. And what you get if you integrate that and evaluate it over the bounds is that f of t is equal to pi over the square root of t squared minus 1. And don't forget, f of t is also equal to this. So now comes the Feynman integration part, where we use the Leibniz rule for differentiation under the integral sign. All we'll do is we are going to take a derivative with respect to t of f of t, giving us f prime of t, a derivative with respect to t of pi over the square root of t squared minus 1, which will give us negative pi t over t squared minus 1 to the 3 halves. Taking a derivative with respect to t of this using the Leibniz rule will give us negative integral 0 to pi of 1 over t minus cosine x all squared dx. Then all we have to do is multiply both sides by a negative 1, and we get that the integral from 0 to pi of 1 over t minus cosine x all squared dx, which is what we wanted, well, almost what we wanted, is equal to pi t over t squared minus 1 to the 3 halves. And we'll just call this j of t, because we already have an f of t. So we'll notice that if we plug in 2 for t into our j of t, we will recover we'll get I. We'll get the answer that we want. And what you get if you do that is I is equal to j evaluated at the point 2, which is equal to 2 pi times the square root of 3 over 9 if you work all that out. So anyway, that's it. Like I said, you can, I believe you could probably evaluate this one without Feynman integration, but it would be difficult. So there you go. That's it. Hope you enjoyed that.